Okay, so streaming has started, so we can start now. About the mock test for NPP, not sure whether we are going to have one. Um, as anyway, like it's going to be on Kaggle. Okay, so what you have to do is you will be given the data set, and on that you'll be having to train the model. So it will not be like some question answering type. Okay, so it will be more like model building. So for that, the best way to practice is just you can choose any data set and try building some models and see how well you can perform.
So the rubrics will be provided before the exam.
Um, Rubrics for what purpose?
Like how we do the Kaggle assignments, like for 5 marks for loading the data sets and all like stuffs.
Oh, that I don't think so. We will be having that because for the MLP we had that for peer review purpose, but here we won't be having that, I believe. Okay, but you will get the instructions what you have to do if something will be there. Okay.
Okay, sir.
Yeah. So we'll be starting with the week 6 part. Okay, so far we have been dealing with the neural network. So generally for our classification or the regression type of problem. Okay, where the case was that we have the data set, we have the labels associated with them, and our goal is to build a robust model which can, given our data set input, can predict closely as the label one. Okay, now in the week 6 and from now on from week 6 we'll be moving towards the generative AI part. Okay, so week 6 will be the introduction to the generative models, like what are all generative models all about, and one specific type of generative models that we are going to discuss today will be GAN, generate Gave autoencoders. So that's what we'll be doing in week 6, and after week 6 we'll be following with the sequence of RNN, encoder decoder architecture and transformers that will come in the follow-up future weeks. Okay, so this is the agenda for today. We'll be starting with a discussion of what is the generative model, then the generative versus the discriminative models. So this is something that we have seen in the MLTV kit, but we will be revisiting this today. Then there's something called as the latent space. Okay, this is the terminology that we are going to use, so we'll be defining that. Then the model that we are going to discuss today, that is GAN, Generative Adversarial Network, and how we train the GAN, and what are the key challenges, and what are the solution that the GAN faces. Okay, so that will be the agenda for the today. And for a starter, we have what is the generative models. Okay, so anyone who has watched the lecture, can you tell me what is generative models?
Such generative models are which can generate the new data basically based this works
Yeah,
on the joint probability.
generate new data. Okay, now our goal is no longer to be classification or the regression part. We want to generate our new synthetic data uh, using our trained model. Okay, now there are ways using which you can do it. One is using, if you find the probability distribution for which, if you assume that your data set X belongs to some probability distribution X. Okay, and from this probability distribution, you can sample uh, any point, and that will be like your newly generated point. Okay, that is one of the many ways in which you can generate the models. Okay, that is using the probability distribution. Okay, now what are the applications or key capabilities that we are going to discuss for this is uh, our generative models can be first, of course, can be used to create the data generation. Okay, we can even use it to filling some values or some missing part from our data set, or missing slash imputation. Okay. One thing for which it can be used is for anomaly detection. And it can be used to in the representation learning part. Okay. So data generation to create new realistic samples. Missing imputation. Okay. So if let's suppose if you have an image and some part of the image is not clear or it's kind of missing, then you can use your generative models to fill in that missing values there. Anomaly detection is basically that from our learned distribution, okay, we create new data and we see that this new data how close it is to the original data point that is there. Okay. And if it is like the reconstruction error that we say some kind of, if it's quite high, then it's kind of like an anomaly. Anomaly is kind of like an outlier. Okay. So generative models, specifically the autoencoders, are generally used for anomaly detection part. Then we have a representation learning part, that is to meaning we can have some well-defined low dimensional representation for our high dimensional data like images. So images, as you know, are very high dimensional data set, because if even if you like have a image of size 200 cross 200, okay, and it's living in a 40,000 dimension. Okay, so we can learn a very low representation of it using our generative models capabilities. Now, how we do that, that we are going to see later, but these are some of the key capabilities that a generative models has. Okay. So starting with the example of 2 cross 2 grid image that Prof took. Yes, Shubham.
So like the mathematical aspect I am not clear with. So can you tell it again, that mathematical aspect?
We have not seen that yet. I
Oh,
am just discussing it theoretical only.
this one, that x is some random data and we are dividing it into the probability distribution. How is this happening?
So what I was saying that here, that we can assume that our data set is coming from some probability distribution. Then of course, because if follows some kind of probability distribution, we can sample from that to create our new data set. Okay. So
Okay.
that's one way. Uh, that way is usually done by the naive Bayes model. It's kind of like to uh, find the probabilities for this data set. Yeah. So for the 2 cross 2 grid image, it's a binary image. So that means the pixel values are either 0 or 1. 0 for the black, 1 for the white. Okay. So it's a 2 cross 2 grid image. Now, with a possible combination that each of these blocks can take one of the two values, either 1 or 0. How many different images, first of all, you can create?
16.
16. Very good. Okay. So 2 power 16 unique images, first of all, we can create. Okay.
2 power 4.
Oh, sorry, yeah. 2 power 4. Okay. Because each of our pixel can take two values. So as we have 4 places to fill in, so 2 power 4. Okay. So we can create these 16 new images, and what we can do is we can basically extract the possibility for each of these occurrence. Like what is the probability that the first pixel value would be 1? So we have all the 16 possible images, and we can see how many times the first pixel value is 0. Okay. And using which we can find the probability. Okay. So in this way, we can like learn the probability for a image or for generating an image here, with the probability that this pixel value should be black or this pixel value should be white. Okay. But one of the problem that will be there is, because it is a very small image, we can go ahead and create all possible combination here, and from that we can sample. But for any realistic image, if I take the example of our MNIST data set, we will be having the 28 cross 28 cross 1. Okay, it's a grayscale image. So it will have 784 total places to fill in. And let's remove the part of grayscale, even if it would have been a binary image again, then for these 784, again, we will be having two choices for each of them. Okay, so it would be 2 power 784 combination. Okay, so that's like an impossible task to do, to enumerate all possible combination and generating the probabilities from there and sampling from it. Okay, so this one example is to illustrate that like we cannot go ahead with the task of enumerating all possible combinations for our dataset and generate the probabilities. So we need something different for generative task. Okay.
So like the above one, you did the manual ways, and you will now tell us how to do it in a generative way.
See, this was, yeah, we did it in the manually based. Now for the generative based, of course, we are not going to go with this manner of enumerating all possible ways. Okay, we'll be using some different methods. Specifically, we will be dealing with the GAN in this week. That will see later. Okay, after some time. Okay, yeah. So a few of the applications that we discuss are here. The first one is, of course, the creating new samples. Okay, so
Sir, can you please explain why you why you took it 28 plus 28 plus 1
uh, I took
to
the
show that
example of
it's a gray sample?
I took the example of the MNIST dataset image. Okay, that image that we had was the 28 cross 28 cross 1, right? It was a grayscale image. That's why the depth was 1, and it was of length,
Yes.
width, and height is 28. Okay, yeah. So first application for generating new samples. So if you are somehow able to learn the probability distribution for the X, then of course from that distribution you can sample any data points. Okay, new data points you can generate it from. Okay, so for our example of 2 cross 2 grid image, you can learn the diagonal. If you learn that the diagonal pattern is like common here, then that image will be most likely to occur if the diagonal pattern image has more probability. Okay. For the marginalization, it's similar to what marginalization meaning that we had in the probability that okay, if I have
Sir,
this.
is that always the case where diagonal these have the more probability to occur?
No. This is some synthetic probability we are uh, assuming that if the probability that the diagonal elements are black has more, then of course it's like the diagonal elements black image has more chance to get generated. Okay. Okay. If I repeat, then what I am saying that assume if you are able to learn a probability distribution for your X, that your data sets are getting generated from this probability distribution. If you are able to figure it out, and once you are able to figure it out, you can sample from this probability distribution for any images. And that images will, how it will be generated, it's like based on the probability. So if the probability for an image in which the diagonal elements are black is high, then the sampled image is more likely to be an image in which the diagonal elements will be black, because the probability for the diagonal images to be black or the diagonal elements to be black is high. Okay. Yeah. Now for the second part, the marginalization. Yes, Karthikeyan.
This probability we will be taking from the available data set or based on
Uh,
the actual data, because we are doing two things, right? We also generate new samples
mm,
from the given data,
yeah.
where this probability will be taken from where?
This probability distribution will be learning from the given data only.
Okay, so from the samples.
Yeah.
And from the samples we generate based on the possibilities, like you have taken the a box with diagonal elements, dark. Yeah, this is one sample, and then we can make 2 power 4 samples based on this, just making ones and zeros, right?
Yeah.
Okay, and the probability distribution for this case is uh, how do we do that? Now the probability for this is only given the sample one, we have one a probability of squares being diagonal squares being black is one. Is it
Uh, so
given only one sample?
no, see, what you will be doing in this case that we were discussing here is like you can enumerate all possible cases for the images. Okay, so all possible cases for that is you can enumerate all 16 images, and from that you can have some probabilities that in your data set this type of image is occurring this many times. Okay, so that will be your probability for that particular image or that particular pixel taking that value. Of course, it's data dependent, how many times it's occurring. Okay, and based on that, you will be calculating the probabilities.
Even the probability is also based on, because I can make any probability, right? Diagonal squares to the right hand side can be black, left hand means
Yeah,
this, the other one can be black
uh,
or alternate black, whatever it is, right?
yeah,
I can make so many probabilities.
yeah. But of course, you cannot make more than 16 possible cases because 16 are the only unique images that you can create.
Yeah, less
For it
than
to
the probabilities will be less than 16.
probability will be less than
Less than
1.
no,
Probability,
probability will be less than 1. The number of probabilities which I can generate will be less than 16.
yeah.
I can say
Now,
whatever things, right, about this diagram.
yeah.
Okay, okay, okay. Thank you.
Now the marginalization part. It's the same topic that we studied in the stats 1 or stats 2. Let's suppose for your same image, okay, you have these pixel values x1, x2, x3, x4. Okay, then if you want to marginalize over x1, that is you want to find the probability for x1. Okay, and it's nothing but if you just sum over x2, x3, and x4. Okay, so all possible values, whatever values you can take for x2, values you can take for x3, and values you can take for x4. If you sum up all these probabilities, okay, by keeping x1 as a constant, okay, and varying x2, x3, and x4, and if you sum that up, that's the marginalization for the probability for x1. That is for one probability pixel value that you are going to get. Okay, so finding the probability for the subset of the variable by either you can sum it up or integrating if you go in the continuous domain. Okay, so this will tell you the likelihood for any specific pixel value. So I took this example, you can take any other case also, not necessary to be x1.
That should be constant, the one we are taking.
Yeah, that on which you are going to do the marginalization. Okay, so you will be varying the remaining ones. Okay, except that. Now the third part, that is the imputation part. So you have one image in which you have only one value is present, and let's suppose the others are absent. Okay, so you have this one present variable and other variables are missing. So what you can do is you can again find the probability that given that my x1 is present, what is the probability for the missing pixel? Okay, so that again you can frame it as a joint probability. Okay, and divided by your marginal of x. Okay, so it's again from the stats part that this conditional probability can be written as the joint probability divided by the marginal probability. Okay. Now again here would be one bottleneck that for this missing pixel, okay, So we have 3 missing pixels here. Okay. So how many images you can generate with x1 being here, but you want to fill in these values. So how many different
200.
2 power 3, right? 2 power 3 here it will be. Again, considering each pixel can take 1 or 0. Okay. Then you can create 8 different images, right? Okay. But again, if it becomes a big image of something like 256 cross 256, okay, then again this will blow up, and in that case again the computational bottleneck will be there to calculate. Okay. So the last part for this, that is the classification part, that your generative some of the generative models can be used to do the classification case also. Okay. So what generally the generative models find is that uh, given the class, some class, how my uh, X will look like. Okay. So how does the dog images look like? How does the cat images look like? Okay. While in the general case, when we are doing the classification, what we generally intend to do is we have given the data point and we want to find the class for this. Okay. So using Bayes theorem, we can basically do this, that probability of X given Y equal to C times probability for Y equal to C. Okay. Divided by the probability for data point. Now this again can be found using the total probability law. Okay. And this is basically the same expression that we have seen in the naive Bayes algorithm, if you are able to recall. Okay, there also, if you remember, the naive Bayes was a generative model, and we use this for the classification purpose. Okay. So this is the same thing that we can do with the generative models. Okay. Clear so far? Okay. Now, one difference between the generative and the discriminative model. Discriminative model, the goal is to find a decision boundary. Okay. Where basically to discriminate between two classes or more than two classes if you have. Okay. While the goal of the generative model is to find the underlying distribution of the data to generate new data. Discriminative models is going to aim for the probability for y given x. Given the data point, I want to find the probability for my class. Generative models for the probability for your data points. The question answer for the discriminative model would be, given this image, is it a cat or the dog image? While for generative models, it's the question is like, what is the image for my or how does my dog images look like, or how does my cat image look like? Okay. Example for the discriminative models are the logistic regression, SVM, our ANN, CNN. Okay. All those are discriminative models. They are used for the classification or the regression task. Okay. Basically to discriminate between the classes. The example of the generative models are GAN, that we are going to see in today week. Okay. Variational autoencoders, the diffusion models. Diffusion models not in this week, but maybe I think after week 9 or 10, we are going to see them. Okay. So that's the difference. Now the main topic for today, okay, will be our latent space. Okay. Till now that was just some background of the generative models and what are their capabilities. But the main point for discussion will start from now on. Okay, that is the role of the latent space. Okay, so what is the latent space? Okay, so far we have seen that we cannot model, or we cannot aim to model for the probability distribution for our entire data set, because as our dimension grows, the computational bottleneck, okay, and enumerating all different kind of possibilities will be very hectic. Okay, so what the latent space do is basically, instead of going with modeling the complex pixel space, we basically learn a small low dimensional space. Okay, So learn a small low dimensional space. Okay, and this space will be used to generate the high dimensional images. So we will basically what we are going to do is we will be trying to find a mapping which map this our low dimensional space to the high dimensional image space. Okay, so our first aim will be to learn this small dimensional space. Okay, now that space is called the latent space. Okay, is it clear?
Just can you give an example about, say, for example, photo
Hmm.
of an elephant.
Yeah.
How the low dimensional space this elephant, how it will be,
Yeah, just wait for a few more minutes.
or any picture,
Yeah, just wait for a few more minutes when we are going to discuss because till now we are only discussing the terminologies. We have not come to the point for model building part. We have not discussed the model yet. Our model is will be the GAN that is going to do that. Till now we are only discussing the terminologies that we are going to use while doing that. Okay.
higher dimensional will become a, we will
Image.
learn a small low dimensional. We have two qualifiers here, small and low. This is
Yes.
what is small and what is low. Low dimensional,
Uh,
okay, because the
yeah.
pictures are higher dimensional. Small means what?
Yes.
Okay, only learn alone. Okay.
Yes, Shiva.
Yes, sir. Like it basically looks like the PCA, what we used to do in PCA.
Yeah, it's kind of related to that, but PCA also like of course we are going to I'm going to take the example of the PCA why PCA also fails to do this because PCA does not learn that much meaningful structured uh, low dimensional space. So that's why we do not go with the PCA.
Like because of
Yeah,
linearity.
but yeah, kind of the analogy is same. The thing that PC used to do is we used to have the low dimensional representation for
Yeah.
our high
Yeah.
dimensional data set. So the
Yes.
analogy is same here.
Like basically it fails because of linearity.
PCA fails with the linearity. Of course, we have the
Kernel PCA also.
workaround for for kernel PCA and the SVD. But
Yeah,
of course,
that's also there.
those are mostly like our statistical method. They do not have that much great capability for generating the high dimensional data as such. And
Okay.
often the low dimensional space that we got from those are often unstructured. Yeah, the
Okay.
next thing is about that only. That our old way that used to have, like our PCA, okay, and that also we had this process. What we had that we have our high dimensional data, and from that high dimensional data, we go from to the low dimensional data. Okay, so in that our goal was the discovery. Okay, we discover this new latent space. Okay, given our high dimensional data, but this was often unstructured, and in the PCA specifically, this was just a shadow or the projection of the original data complex structure. Okay, so this does not use to give good result or produce or capable of producing high dimensional data objects such as images as such. Okay, now the new way the GAN that used to work is it goes in the reverse direction. We have this latent space noise. Okay, we call it noise because it's randomly generated data point. Okay, and from that we go to our new data set that is we are going to generate. Here the goal is generation. Previously the goal was discovery because from high dimensional we are going with the low dimension. Now we are going in the reverse order. We have the low dimensional input and from that we are going to generate high dimensional data.
So like in the previous like the previous way we were doing the PCA, we were using it and we basically were reducing the dimension and using it for our predictions and all. So that you are referring as a discovery part, or we are not, I think, predicting something with that. But here we will use that data to predict something more, like the with the original data sets. Is that correct?
Sorry, can you repeat?
Like the main thing is like in PCA, what we used to do, we reduce the dimensions from high to low and use it for our model building and all. But in
Yeah.
this case, in this new this noise to the new data, in this case we will be reducing it, and from that we will be generating the whole space of the data.
See, we will not be reducing it. What we'll be starting is with this with latent space. Okay, we will be starting this random noise vector. Okay, and this is basically coming from some probability distribution. We generally take it the normal distribution. Okay, so what we are going to do is we are going to sample from our normal distribution, 0 mean gamma square. You can take any other mean or gamma square also. From that, we are going to sample one point z. Okay, that will be our latent vector. This is called as the latent space from which we are sampling. So that's why it's called as this well behaved probability distribution. Now this sample distribution or this sample data point, which is called as the latent vector, this is our noise z. Now we will pass it to a generative model. Okay, that is again a neural network. Okay, that will output a high dimensional data set such as images. Okay.
Okay, basically, okay, then Z is not the one which is generating it. It is basically going to that model and it is predicting it or
That
generating
is
it.
your that low dimensional representation. Okay. So the thing that I said here that our generative models can be used to in the case of representation learning because it gives us a meaningful low dimensional representation, just like PC used to give, but PC1 is not that much powerful than this generative model. Okay. So now this Z we are going to feed into some generative model that will output us our
But
new
this
data.
Z is but this Z is in the low dimensional space only. But this Z
Yeah.
is in the, so why we're not using that PCA? Because both are using these same technologies only.
No,
No,
both are not using.
Fulkit, I have a basic doubt. Is PCA low dimensional? PCA is principal component. We identify the principal component because
Yeah.
most impact will be on those components. We will take first few components so that it reduces our effort, right? I have
Yeah.
10 or 15 dimension. Not all this dimension impact my label or impact my the final output, whatever it is. We are it's a classification or regression. We will tend to identify what are all the key dimensions affecting this. This is what we do in PCA. We are not studying anything in the lower dimension. We are identifying those dimensions which are having maximum impact on my result. That is
Yeah.
what we do in PCA. So from there, you try to explain us what is this CAN is doing.
No,
In
no.
PCA, we don't do anything on the lower dimension. We are not. We identify only those dimensions which has serious impacts. Oh, 70% impact, 60% impact, 50% impact. So that we work only those few dimensions and then model my, because those things are enough to model. Correct?
Okay. So in PCA, we have our high dimensional data set. Okay. Now, using our principal components, we project our data set into low dimensional space. Okay. Now, that low dimensional data can be used to further any downstream task. Okay. That was the goal of a PCA. Okay. Now, in that process, of course, you will be getting a low dimensional representation. Okay. So as we are discussing here that talk about this low dimensional representation, that's why the PCA come here into the picture because PCA also used to have this low dimensional representation. Okay, but we are not going to go with the PCA because it's more of like a statistical method that is not able to generate that much of a good quality of high structure data. So the latent space that PCA has, the latent space of PCA is nothing but the all the principal component that you have taken. Okay, the vector space of that is the latent space for our PCA. Okay, that's often unstructured to generate new high quality data or new high dimensional data. Okay, and it was more of like a shadow or the projection of our original data set only. Okay.
Sir, can that be because in PCA we lose the original space, right? Because the new principal component that we received was a linear representation of the original one. So we lose
Yeah,
the
of course,
original.
linearity is also one issue. Often, what happens in the high dimensional case is if you see, uh, if I take the example of 200 cross 200 image, okay, it's say 40,000 image, 40,000 dimensional data. Now, among these 40,000 dimensions, only very few images are the meaningful images that you can create. Others are just some random garbage images, right? only with certain pixel arrangements you will be getting a meaningful images in such high dimensional case. Okay, and that's the usual thing that will going to happen in such high dimensional objects.
You mean to say the background is not having any meaning? The image
I'm
of
going
cat
the
or
image
image
itself
of
will not have any meaning. It will have just random color pixels values and nothing more than that.
no, this 40,000 pixels.
Hmm.
There are pixels which will be background, and there are pixels
Uh,
which might be the object of interest, a cat or a dog or a
let
person or
me
something.
show you something. Okay, so we create a image of hmm, so we have this IMG, which is a 200 cross 200 random pixel values that I or the random some array that I created. Okay, now you can pass it to uh, our matplot mshow to showcase this image. And okay, this is what I meant by a random garbage image. Okay, because the pixel values are just randomly generated. So in such high dimension, most of the images that you are going to create will be something like this. Okay, some random garbage image is going to get generated. Only with certain pixel arrangement, you are going to get a meaningful image. By meaningful images, I mean is something like okay, like this. Okay, a meaningful image is something which a human can make sense. Okay, these kind of images are only with certain pixel arrangements only, right? Only when a certain pixel arrangement is going to we are going to get values here, only then we are going to get the image of this nature scenery. Okay, otherwise with just some random pixel values we are going to get some kind of this garbage image. Okay, and that's often the problem with the high dimensional data because in that such high dimensional most of the only like most of the space is just filled with garbage image. So we want to find a meaningful or we want to find a generate a meaningful images. Okay, and that is done using this new process that is in which we have this low dimensional input first, which we are going to feed into our generative model, and that will give us just a high dimensional data, or that is our image. Now, how we do that, that we are going to see a little later in the GAN part.
So that is a latent space, sir. That
Yeah, the low dimensional is our latent space. Okay, the
so
low
that is
dimensional.
so that is basically different from PCA, as you have told.
Uh, See, in PC also we have this latent space. The latent space of PC is the uh, projected or the our PCs that we are taking, the principal components. That was
Yeah,
our latent space for the PC.
yeah.
Latent space is basically, if you understand it in simple term, it's just a low dimensional space. Okay, and the vector in that low dimensional is the latent vector.
Okay, and this new way is known as the GAN. This new way.
Uh,
The
oh no, no,
vector.
not just the GAN. It's just how generally we are going to deal with the generative models. Okay, in which we are
The
going.
term. What is the term actually? Like the term is what? If it's not PCA, then what is the term?
See, the term for our vector or the low dimensional representation vector is the latent vector and the latent space. Okay. Now the process might differ from model to model, how it uses this latent space or latent vector. Okay. In the week 6, we are going to dealing with the generative adversarial network GAN. Okay. GAN has this process in which it's going to take this latent vector and pass it to a neural network that will produce us the image. Okay. Now, in the later weeks, maybe we can see the diffusion models, which will have the different process of doing the things. Okay, so that might differ. Okay, clear so far? Okay, so the final note that the pre-deep learning era that we had, okay, these models that we had, the PCA sub SVD, okay, so these are also used for the finding the low dimensional representation, but they often struggle with producing the high dimensional data back to us. Okay, so that was one side of that. But in the case of our new way of the generative models, we find this latent space, okay, which is nothing but a probability distribution. Generally, we go with the Gaussian distribution with some mean and the variance. Okay, we sample some point from there. Okay, and then we learn a mapping from this simpler continuous distribution. Okay, to our data set. Okay, so from this our Z that is sampled from some normal distribution, we will learn the mapping that is going to generate our data set. Okay, that mapping is what we need to learn now. Okay, and basically the same intuition is written here that I spoke about just now, that the space of all possible images are basically quite high dimensional. So if you just randomly pick some point from there, then it's not going to give you a meaningful image. Meaningful images basically means a image from which a human can make some sense. Okay, so our ideal choices would be we pick a smaller space, okay, and then we train our model to decode that space into some meaningful image. Okay, so clear so far?
So here you are trying to say you are trying to take the same example on the first where we took a square of 4 boxes, and then where we are having only sample space is total 16. But if I take a picture of an elephant which is having 200 cross 200, in that case it will be exploding the number of samples, and it will
Yeah.
be random, and it is very difficult for us to make sense of the picture of that elephant. So we are trying to take the Z. That's what you will explain. The Z is what is going to help us um, uh, taking things from random, and then if we learn this function, then we can get the elephant quickly.
Yeah.
This is what you are trying to say, yeah?
Yes. Not quickly,
Like, or meaningfully.
meaningful. Yeah.
We will. So in general, this is the story you are trying to narrate, yeah?
Yeah. That
Okay.
the high dimensional data set, enumerating all possible combination is almost impossible. First thing, even if we go with the low dimensional representation, the pre-deep learning era that we had, the options that we had was the PCA, SVD, but also these models also struggle with the high dimensional data. Okay, so discarding all those options, now we have this new option of the generative models, which will learn a mapping from a low dimensional latent space to high dimensional images. Okay, and the low dimensional image space is coming from this some simpler continuous distribution that is generally chosen as the Gaussian. Now somebody asked how we choose this mean and sigma. Usually you are going to fix with some mean and sigma. Okay, now these are something experimental, but usually you are going to fix some mean and sigma. Okay, and or like after that you're going to train the model. Okay, because the main thing that is dependent is this model capacity. Okay, how this model is going to train, because that will be our mapping from this low dimensional to high dimensional. So it's not more focused on with what mean and sigma we are sampling from. It's more focused on this mapping part. Yeah. Now few more terminologies that are there is our generative models. Okay, these are classified into two parts. One is the explicit density models, another is the implicit density models. Okay, so I know this week is mostly theoretical. That's why these much theory is there. Is it random? Like mean and sigma? Yes, they are random. Okay. So explicit density models is basically these are the models which allow our direct evaluation of the likelihood. Okay. So now this includes the autoencoders. 1 minute. Yeah. And gradational autoencoders, we have not seen both of them in the course, so don't worry even if you do not get what are these. Okay. But these two models are basically the example of explicit density models. Okay. While our implicit density models are basically the models which learn to generate data without defining the probability function. Okay, so without our defining the probability distribution for the x, they learn to generate data and sample from this. Okay, and the example for that is our GAN that we are going to see. Okay, so this is mostly like just the classification. Okay, we have two types of generative model: explicit and implicit. Explicit basically try to learn this likelihood distribution for the probability of x, while the implicit one, like the GAN, it does not. Okay.
So what is this direction evaluation likelihood? What is this?
They basically learn this distribution. Okay, the autoencoders and the variational autoencoders, they learn the distribution here for the probability of x. Okay, just like we were doing the things in the naive base. Okay, there also we were learning the distribution for the our data set. Here also they try to learn. Now there's one more subclass in the explicit density models. Okay, that is the autoencoders models are basically the one that try to fully learn the likelihood, and the variational autoencoders are basically try to approximate the likelihood for that.
Any commercially available autoencoders we have, or we like GPT and all, right? Gemini.
No. The
Do we
state of
have
the
it?
art models are not. The state of the art models currently are the diffusion models.
No, no,
Okay.
I understand that. Is there any commercially available autoencoder models we can refer?
Not that
See,
I'm aware of.
autoencoders and VAE are explicit. Is it available currently today? Is it there? Anything any application, any models available? Like I
Models
just
you find on the Hugging Face.
okay. I just have to Google for
Yeah.
autoencoder model like that. Okay,
Yeah.
I'll do that.
So this GPT and all uses a GN type techniques.
Not
Implicit.
the GAN. They use, I think, the diffusion models. GAN is also not used now as such. Okay.
So diffusion
Currently,
is a generative model.
yes, diffusions are the generative models. We have
Okay.
not studied the diffusion models in this week, but in the lecture, the prof was saying that we are going to study that, but maybe I think in the later part of the week. So maybe in week 10 or 11, we are going to see that. Okay. Yeah. So now is the time when we are finally going to define our generative adversarial network GAN. Okay. So the GAN is basically kind of like a game, you can think. Okay, so the analogy for the GAN is the artist versus critic. Okay, so this analogy means like generally what we have, that we have an artist that's going to present his art, and then there will be one critic which going to comment on the art that is made by artist. Okay, so the artist is our generator and critic is our discriminator. Okay, so the GAN actually trains two neural network. One is called as the generator, one is called as the discriminator. And what it's going to do is it's going to stand these two neural network opposite to each other. So it's going to tell them fight each other, and in that fight, we hope that both of our network, the generator and the discriminator, will get better and better. Specifically, our generator will get better to generate images. Okay, so we will have this generator which is going to generate our images. Then we will be having this discriminator which going to discriminate, or which going to tell whether it is a real image or a fake image. Okay, so
So can we say that discriminator is basically optimizing the generator?
um, kind of you can say. Okay, but of course in that process it's going to train on its own also.
Like the
Okay,
theory part, for the theory part, like
it's
discriminator is
say
basically.
both of them like fight to each other. Okay, so for one success depends upon the other failure. That is, if generator going to get success, then the discriminator is going to get failed. If the discriminator is going to get succeed, then the generator is going to get failed. Okay, so both are fighting to each other to get better. So that's the game here. Our G, that is our generator. What it does, it takes our random vector Z. Okay, and the goal is to create fake data or fake images. These are called, for the terminology, we will be calling this as Z of Z. Z of Z means it is the output by the generator. Okay, and it has to generate images in such a way that it can fool discriminator. Okay, so it has to generate the images in such a way. Our second neural network here is the discriminator. That is our critic. Okay, now this is nothing but our standard classifier. Okay, the same classification models that we have built at the time of the MNIST dataset. It's just similarly like we are going to build a normal classification models. Okay, and the goal for this model is to distinguish between the real images and the fake images. Okay,
The CNN and the NNs, the CNNs and the NNs.
see, if we are going to do with the images, you can take CNN also here in the discriminator. No problem in that, right?
Okay, we need to use the neural networks only for that, but not the randomized models like the SVD and all.
SPD is for low dimensional representation. We are not going to use that. We are going to use neural
No,
network only.
just for the example, like we need to use the like the artificial neural, like the neural networks only for this.
See, you can use the simpler one also, but of course they will not have that much capability. You can use the same idea for there also, but again the issue will be regarding the quality that you are going to get. Okay. So yeah, I hope the game is clear. Okay, we will be having one artist. We'll be having the critic. Artist that's going to show his art. Okay, and our critic is going to decide whether it is the real art or the fake art. Okay, so artist is our generator, critic is our discriminator. Okay, so generator going to take a random vector Z from our latent space. Okay, and it's going to create fake images. and the images should in such a way that the discriminator cannot discriminate between the real and the fake image. While the discriminator task is to get better and better in distinguishing between the real image and the fake image.
So by real images, do we mean the images that we have given as an input?
Yeah, that we will be having some real image data on which it's going to get trained. So those are the real
Okay.
images. Okay. So suppose you have this MNIST data set in hand. Okay, you are going to use those images as the real images. Okay.
So can we generate a 4K data with this kind of discriminator, like a 4K clarity data?
That much good quality might not be possible with GAN, I think. Okay. So with that much high quality, you need maybe the diffusion models. So GAN might not be able to give that much good quality. At least the
So,
vanilla GAN framework will not be able to give.
so what do we need to generate that much?
We need some more complex model like diffusion models.
Okay, okay, okay.
And the variants of the gains are also there, like the style gain by NVIDIA.
Okay, okay.
Those also are like increase the performance that can.
Okay, sir.
Yeah. So
Got it.
before
Sir,
moving ahead, yeah.
and hardware kind of thing, how much hardware is needed to generate that kind
Uh,
of?
Hardware, of course, they need a good amount of computation resources to get trained, and specifically to be good at creating good amount of images, they need a good amount of data also. So
Any guess about how much hardware, like the Nvidia chip, like how much it should be? The
I do not have any guess for that, but you can maybe find something online. You can search.
okay.
So are we going to do the diffusion models and all?
Not in this week, but maybe later week.
Okay.
Sir,
Yeah.
the
So is
diffusion models is mentioned here in the 6th week too, right?
yeah, sixth week also sir is mentioned because it is a part of the generative model. Okay. So for the example of the generative model, it is mentioned, but we have not defined it. What are the diffusion models?
Okay, we have not gone on with the working of it completely.
Yeah.
Okay,
Only the GAN is discussed in this week.
okay, sir. Thank you, sir.
Yeah. So before moving ahead, is the analogy clear? What's GAN going to do? Okay.
So this week is entirely for a 6th week, right?
Yeah. This is for the sixth week.
And will there be any extra sessions for like NPP?
Not from my side. This is the only session that I'm going to take this week. So not be discussing anything apart from the week 6 content. Maybe instructor might do. Okay.
Okay, sir.
So now a little bit mathematical part for the discriminator function and the generator one. Okay. So both of them have their objective function that they want to maximize or the minimize. So the discriminator that our classifier tends to maximize this function. Okay. Now if you study about it, d of x is basically the output of the discriminator. Okay. So it has given some input. Okay. That input is sampled from the data set only. So because it is sampled from our real data set, okay, the d of x should be classified as the real image. Okay, so it's going to output your probability. So the log of probability we are using because the probability values are low. So like accumulating very low quantities can make the numerical computation unstable. So we take the log of that and we are averaging over that using the expectation. Okay. So what this entire term represents is the correct or the real images are labeled correctly or classified correctly as real. Okay. While the second part, as it says that we are sampling from our latent space. Okay. We are sampling from our latent space, passing it to our generator to create the fake image, and then passing that image to our discriminator. Okay. Now, d of something is basically the probability for classifying it as correct image. Now 1 minus d of that would be the probability for it to classify as fake image. Okay, so we want to this probability that the probability that it's going to correctly label the fake image as fake. Okay, again the averaging over all the possible things that we have, and we want to maximize this entire thing. That is, we want to maximize the probability for real image to be classified correctly and the fake image to be classified correctly as fake. Okay, we want the sum of these two to be maximized. That's the goal of discriminator. For the generator, okay, now this expression that is there inside, it's basically the same as this expression. Now, of course, the goal of this is to minimize this. Why? For the generator? Because if this quantity will get minimized, then that means this quantity will be get minimized. That is, the probability for classifying a fake image as fake will be get minimized. If that will get minimized, then what will going to get maximum? The probability for fake image to be classified as real will get maximum, right? Because one minus of that is getting minimum, so this quantity will get its maximum value in that case. That is the goal for the generator, right? Because it want to classify its fake image as the real image.
Here, both the fake and the real image will be generated by the generator, is it?
No. Generator is going to only generate the fake images. Real images we already have as our data set.
Okay. So why we should take the real image into this maximization?
This is for the discriminator case.
Discriminator.
In the discriminator, we want both the images because we want to train our discriminator in such a way that it's going to correctly classify both the real images, real image, fake images, fake image. So there we need both the
training. So the training will take some portion from this data set, real data set, and some generated by the generator.
Yeah.
Fake images.
Yeah. So we are going to come this training loop, I think. Yeah.
Okay. Then okay.
At that point, it will be more clear. Currently, we are just discussing the objective function. Okay. That's for the for the discriminator. The objective is it want to classify both the classes correctly. The real image is real, fake image is fake. The objective of generator is it wants to minimize this. That is the probability for a fake image to classify as fake. It want to minimize that probability. That is same as maximizing this quantity. Okay, maximizing the probability for a fake image because G of Z is the fake image to output as real image. We want to maximize that. Okay. Again, the label 1 means it's the real image, 0 means it's the fake image. Okay. So these are the objective functions for the discriminator and the generator. And we can basically combine these two as the min-max problem we can create. Max over D, min over Z, and together we can call this. That's the full training objective for our GAN, in which discriminator will aim to maximize its objective function to correctly label a real image as real and fake as fake, while generator will try to fulfill its part of minimizing the objective function to classify a fake image as fake. Okay. Now, because these two networks are logged in the competition, okay, so this thing I said that one success depends upon the other's failure. If generator gets success, then it's the failure for the discriminator because discriminator is not able to distinguish. If the discriminator gets success, then it's the generator failure because generator is not able to create such images which discriminator is not able to distinguish. So one success depends upon the other's failure. So this is called as the adversarial learning. That's why the A in the GAN stands for the adversarial. So generative adversarial network. Okay. It's a generative model. It uses the adversarial learning method in which we stand our two neural network in the competition in which one success depends upon the other. Okay. Now, the ideal outcome of this entire game.
What is the threshold for this success and failure? When
Yeah. Yeah,
we say this is
Yeah,
fail and this is
that's what we are going to discuss now.
okay.
The ideal outcome. Okay. So this ideal outcome of the Arctic versus Tritic game, okay, is to find the Nash equilibrium. Okay. This is basically the point when generator produce such good quality images that the output of the discriminator for that is around the 50%. Okay. That is for any images that is getting generated by the generator. If you pass it to the discriminator, it's going to output you as 0.5 probability that it is real. Now, because 0.5 is the worst case scenario for you. You have 50% chance that it is real, 50% chance that is fake, which is no use of us, right? So this is the ideal scenario that we consider, and that's called as a Nash equilibrium state. Okay.
What
When
is the background for choosing 0.5?
as I said, 0.5 is the worst case scenario for you. It's the 50% chance, right? If you have the probability like 0.4, then of course you have a real, if this is the probability for classifying it as real. Okay. Then uh, this is still good. Okay. But in the case of 0.5, it's worst because you have 50% chance for the real image and 50% chance that it is a fake image.
My question is, Pulkit, how, on what basis they come to 50%? Why not 75? Why not? We expect to have 100%, right?
See,
Expectation.
50%,
Okay,
if
that's a
you
very
are,
ideal.
no,
100%
no,
is very ideal.
if you are
90%, 95%. Why 50%? This is what is my question.
50% probability for all inputs. So this is the probability that a image that is getting generated by a discriminator is a real image. So if you are saying that you want the threshold value to be 75, then for any image generated by the generator, the probability that it will be a real image is 75%. And it will be a real image, right? Because you are saying it with 75%.
Maybe this is defined by that industry for image generation. 50% is because I'm not an expert of finding the image. Maybe 50% of my image is sufficient to identify me. This is from where this
50,
50% came. Maybe image is image of yourself. If it is 50% developed by the generator, that is sufficient, means then 50% of your image anybody will be able to identify. Pulkit, this is what is the question.
no, 50% is here the probability for the discriminator. Okay. The output of the discriminator will be a probability between 0 to 1. Okay.
Yeah,
That
he will
probability
say
will,
50% full kit, right? He will say 50% this can be full kit. This is what
no,
discriminator will say, right?
yeah, 50% it can be Pulkit, 15% it cannot be Pulkit. And that's the worst
Yes.
case scenario, right? Because you are at the midpoint. Okay. That
Okay.
is kind of like a random. A random guess can be more better than that. Because a random value you can take like in which you can be more sure in which part you want to go. At a 50%, you are at the middle line. Okay. In which in both the case of real and fake, you are at the between midpoint. But if it would have been the case like you have the 80% confidence that it's the image of me, okay, then that's a good scenario, right?
Okay. Thank you.
Yeah. Okay, so how the gain is going to get trained? Now we are going to go in that direction. So we are going to train two neural network here in our loop. Okay, so alternatively, we are going to train them. We start with the discriminator part. Okay, so for that purpose, what we do is we are going to freeze our discriminate generator. By freezing our generator means we are not going to update the weights for our generator in this part in the phase one. We are just going to update the weights for our discriminator. The same thing will happen when we go with the generator training part. We are going to freeze the discriminator. Okay. The next step is get a batch of real images, label one. So if let's suppose you have 1000 data points, you are going with the 5 batches in which 200 images each batch. So you are going to take the first batch, okay, in which you will be having 200 images. Okay. Now, of course, because this is the real image that you have in hand. Okay. So you are going to label all of these 200 images as 1. Okay. Then you are going to create the same 200 images more. Okay. With label 0 that is created using generator. Okay. Now the next step is we train this on our D. Okay. And our goal is to maximize the the discriminator objective function. Okay, just 1 minute. And what we want is basically the critics should get better at spotting the fake images. Yes, Shubham now.
So you are telling this as a phase 1 part. So in phase 1 we are freezing the generator G. So in the second step, how can we take the images from the G, because we are freezing that generator?
In the second space, we will go and backprop in the generator, but we are not going to backprop in the discriminator.
But we have
Okay, what
written there freeze the generator. Yeah.
freezing generator only means that we are not going to update the weights for the generator while doing the backpropagation here. Okay. Freezing only here means just in the case of updates will not happen or the gradients will not backflow with generator. Okay.
Okay.
Yeah. Freezing does not means like it's not going to give you the output or something. It only means that the gradients will not flow back for the generator. Okay. It can gives you the output still. Okay. For any random z vector that you are going to give as an input to the generator, it's going to give you an output, but it's not going to get updated. Okay. In the phase 2, we freeze the discriminator. Okay, this is the reverse case that we did for the discriminator part. Okay, now we generate a new batch of fake images. Okay, and then we pass these fakes to D. Okay, but this time we set the label of these images as 1. That means let's suppose if I again take the 200 fake images that are generated by G. So we are going to generate 200 images, but now the label of these images would be 1. Okay, so we are labeling our fake images as the real image and passing it to our discriminator. Okay, and again our goal is to minimize the generator objective function. Okay, so we are training in such a way that our generator will be able to classify or will be able to get these images that it is creating as the real image. Okay, so this is the phase of the generative training. It has 2 phases. The first is we are training the discriminator, in which we have the batch of real image. Okay, with the same batch, we are going to create some fake images from the generator, but we are going to label them as 0. Okay, and train our discriminator. Okay. In the generator training part, we generate a new batch of fake images, but this time we will label them as real image. Okay, and with that label, we are going to train our generator model. Okay. Yeah. So that's
Sir,
This
are we
part
going
is
to
not clear.
solve some numericals?
Numericals, I do not have anything, but it makes time numerical you can take for any practice assignment case if you find any difficulty and ask on the discourse. Okay.
Pulkit, this generator portion training, I'm not clear. Discriminator, a little bit clear, because you take the sample, label it as 1, you generate some fake from the generator, label it as 0. Training the discriminator, yes, it's good. Here in the generator, while you are training,
Yeah.
pass these fake to D. You make a new batch of fake images. So it
Yes.
is generated by the generator. So it is fake. And
We
then
know it is
labeling it as 1, meaning how we
because
can, it is a fake image, right?
yeah, but we want our generator to train in such a way that it should create the real images, and that's why we want the label here to be 1. Okay.
Yeah,
Such that our current discriminator.
okay, then there should be something for the generator to generate the fake. It has to see something in the sample of real image to generate fake image. Unless that happens, how a fake
See,
image
we
I can
have
label it as
we have
1.
this discriminator, okay, which will tell us whether the image generated by the generator is real or fake. Okay, now generator will give me 200 as fake images, okay, and I am claiming that these are the real images and give it to discriminator. Now discriminator, it's going to discriminate whether this image is really a what a fake image or the real image or not. Okay, now of course in the initial training part, because the generator is going to produce more garbage images, okay, because it's going to take some time to get uh, start producing some meaningful images, it's going to give a high loss, okay, but when the training becomes stable on the later part, okay, it will be able to generate a good image in such a way that the discriminator will not be able to classify the image generated by the generator. Okay. Is it still not clear?
It's okay. It's okay.
Okay.
Because maybe something we need to do. Maybe we need to see it how it happens. No,
Yes.
we have
See.
not seen. Maybe we need to go. Maybe in the next week. Next week, maybe these things will get more clear, I think.
It's that the implementation also we cannot show it fully because training again takes quite a lot of time.
No, some kind of a theory, because here, right? Because when we are doing all our discriminative learning, right? All those models, where there is a prime a mathematics involved. Okay, this is how something is learned to classify right or wrong. The same way regression, this is how it is being learned to say this is the value, right value or not right value. Like that, there is a mathematics here. There is no, there is mathematics. It's all fully probability, right?
Mm-hmm.
Mostly probability, and then we need to. It's everything is on the air only, like a story. And this portion, I'm still not make myself to convince that this will train the generator better, because generator is doing fake images. And think of from the start, right? You start training the generator, how it will be. It will be doing, and it doesn't have some reference of a real image also. It will take, as you said, from the Gaussian mean zero and with some standard deviation. It will try to get those, it start doing something. And then you make it as 1. From there, how it will improve? Because it is, it will be a garbage, right? How, without knowing full kit, I am drawing, this is how full kit, assume I am an artist. I have not seen you. How I will start and then go to a in future time I will draw full yourself completely. How it's possible?
You do not know, but let's
Yes.
suppose I am the discriminator here. I know how I look. Okay. So I'm going to tell whether the image that you generated is correct or not. Okay. Now, of course, in the initial part, you will be getting wrong. Okay. Then you will keep on improving. Okay. You are going to give me new image. I'm going to see, okay, this you are this much correct. Okay. This
How he learns the weight from you?
Where is that feedback?
okay. So I'm not sure
There
how
should be a
much.
feedback, right? In that case, you come to that point, right? A discriminator is there. He should feedback, right? No, we will not go into this. This will we'll go to the theory, your slide. You show us the feedback there.
See, the feedback is only based in the form of the loss that you are going to get from the images generated by the generator. That's the only feedback you have. Okay. You are going to generate the images from the generator. Okay. And you are going to label them as 1. Okay. Then you are going to feed that into the discriminator. Okay. Now discriminator knows whether it is a real image or fake image. Okay. Now the initial image might be garbage, so discriminator can classify them as the fake images. Okay. But because you
So
label them as
that will come to generator again, you mean to say?
because the discriminator will label them as the fake image, but your true label
Okay.
that you put there is the real image. Okay. So now the back propagation will happen. So the weights for the generator will get updated. Okay. So see if you see the
So
RTB
every time
pattern,
he does a new image, he make it as one, label as one. He send it to the discriminator. The discriminator, after seeing it based on his learning, he will change it to 0 initially to start with. This is the first iteration. This 0 will come, then this fellow will change. Generator will change his weight and then make a new image and then send it. Like this.
again it's going to send it with the true label 1. Okay. Now the discriminator is again going to do the discrimination for this new image. True label for this fakely generated image is 1 again. Okay. But based on whether the discriminator is going to give this as the fake image or the real image, it depends. Okay. So if it is again going to output it as a fake image, okay, with high probability, then again the loss could be very high. So again the weights will get updated more frequently. Okay. So slowly with this training, the generator will get better. Of course, in this case, what happens with the usual problem is that we are going to discuss it.
So
What
there
are
will
the
be a chicken and egg scenario, right? Because you said step 1, first you will train the discriminator.
Yeah.
Step 2, you said generator. How my generator, if my generator is not trained, how my discriminator will ensure that it will
you
find the
have
fake
initialized
image?
both of your network. Sorry. Okay. So okay.
You understand
You
this
have
problem, right?
yeah.
Chicken egg.
I got your point. Got your point.
Okay, okay. If you can
Suppose this is your
briefly
discriminator
touch
class.
upon.
Suppose this is your discriminator class. Okay. You have this your linear model. Okay. In the same manner, you will be having your generator class. Okay, which will take your latent space, pass it to leaky ReLU, then some linear layers, and finally it's going to give you output. Okay. So you initialize both of your model. Okay, and in both the case, what you are going to do, you are going to take different optimizer. Okay, there will be a different optimizer for the discriminator, different optimizer for the generator. Reason because we do not want to update the weights of generator while we are training the discriminator. Same, we do not want to update the weights of discriminator while training the generator. That's why we set different optimizer for both discriminator and the generator. Okay. Then this is the training loop that we do. For each batch, we train the discriminator, compute the loss on the real image, compute the loss on the generated image, update the D parameter. Then we do with the generator, generate the new sample, compute the loss based on the classification of the D. How my discriminator is classifying my real images, my fake images generated by the generator. Based on that, we are going to update the parameter of G. If I show you the training loop that happens, we will be having the images. Okay. Now we have the real images here. Okay. So for the same batch size, okay, the torch dot ones. Okay, what it's going to do, it's going to produce the vector of ones. Okay. So for all the real image, we are going to give them the label is real. For all the fake images, we are going to give them the label as fake. Okay. So first we are going to uh, pass the real images to our discriminator. We are going to get some output. Okay, and here we are going to use a real label because these are the real images. So this is why it is the loss real. This is the loss that we are getting, okay, while passing the real images to the discriminator. Then we create this Z that I was talking about, sampling from the normal distribution with the same batch size and some latent size. This is something that we set from our side. Okay, latent size is basically the size of low dimensional space. Okay, we can set it to 100 dimension or whatsoever. I think 100 was used here. Okay, so we are going to now generate the fake images. We will pass this Z vector, okay, technically it is a matrix now, to the generator, using which we are going to get the fake images. Now we are going to pass these fake images to the discriminator, of course with the detach, so that we do not back propagate through Z. Okay, we freeze the weights here. Okay. We are going to get the output. Now this is the output for the fake images. So that's why we want to use the fake labels here. Now this is the loss for fake images. The total loss for D is defined as the loss from the real images, loss from the fake images. And with that, we update the weight for the discriminator and reset the gradient and all. For the generative training, we create a new batch with the same batch size. We create new images now. Okay. Now the new images are created, new fake images are created. We will pass that new fake images to the discriminator. We are going to get the output. Okay. Now that output, we are going to now label it as real because we want the output of these fake images to be now get classified as real. We want this. Of course, in the initial part, this loss will be very high because initially the discriminator will easily able to discriminate between a fake image and a new image because initially the images that the generator will going to give will be very garbage image like the one that I show you here, kind of here, because it's going to just randomly generated. Okay, so initially the images will be very garbage type image. Okay, so that's why the initial loss will be very high because that output for the discriminator would be real while you are using the true label as the real image. Okay, so the output of the discriminator would be fake while you are using the real label. Okay, so the probability or the cross entropy loss that you are going to take here, the loss value would be very high. So of course, it has to back propagate and update the weight for the generator. Then after updating the weights, you are again, let's say, running through the next cycle, and then again, let's suppose you come into this stage. You're again going to generate the new batch images, new fake batch images. Okay. Now again, you are going to pass that to the discriminator with the real label. Okay. Now, of course, there would be some improvement now because from the last cycle, when it got lost, the weights are updated. Okay. While back propagating it through. Okay. So of course, there will be some improvement here. Okay. So the feedback that you were saying is kind of coming from the discriminator output. Okay. Now again, you are passing it these fake images as the real labels. Again, now it's going to get some improvement, but it might happen that it might not get all of them be like, correctly classified. Okay, so again, you are going to get the loss. Again, the weights will flow back to the generator and against the weight will get updated. And based on that, again, the new set of images will get generated and this training loop will continue. Okay, so that's how the things happens. Now, yeah, this is something that you can see while I train this network. Okay, so initially the D loss that you can see was very low, while the generator loss was high. Okay, that for any image, okay, it was correctly able to classify it as with 99% as the real images. While for the fake generated image, okay, the probability was like 5% or something only to be classified as real image. So for this initial probability was low because initially your images will be more likely like, fake, more fake images will be there. So of course the discriminator will easily able to distinguish between them. But as you move ahead in the training, okay, this loss or the generator will get updated, the weights will get updated in such a way that this probability is going to get increased. Okay, so see now 0.2 point something. Okay, so it's not trained for so long, but now it's like 0.29. Okay, so is it any more clear or is it still the same?
Better, Pulkit, but you are in a very high dimension. You are in a very low dimension. Take some more time.
Yeah, of course, I can understand that. See, that's one major problem with the deep models that we do not have much power for the visualization. The visualization and the imagination power for these models are quite low.
Some kind of a 3D, maybe we will check with Levin also. Maybe if you guys can find some kind of 3D, we can see it right visually, because these are all theory slides and then codes. Yeah, visually, if someone can show both the generator and this how it is, then our understanding can enhance. It can enhance our understanding.
Yeah. So
Something visual is better. Maybe we can see what we can hear what you say, but not fully 100% what you say is not going inside.
okay. Yes. So it's some this.
Sir, I also found the same thing. This is Google Can Live, right?
Yeah. Yeah. Yeah.
I just pinged
This
you
you
on
can.
YouTube.
Yeah, this you can try it out. Okay. I will maybe share the link. Okay, and
Sir,
we play
I
our.
have shared from YouTube. Can you please, can you please open that link and if you try to explain from there?
That won't be possible here. Uh, because of the copyright issue, as this video is streaming also. I'll not be able to play it. For that, either I have to stop the streaming and then only we can do. So that you guys can watch, and if you have any query, then you can ask. Next, I can go ahead with this part. So this is something that I found. Okay, take this noise, feed it to the generator. Okay, then creates the real label, then feed it to the discriminator. I'm not sure how much good visualization it's going to give you. And try this. Yeah, but I can understand your guys' problem that initially these topics will be very uh, hard to understand. Okay, because we do not have much of the visualization when it comes to the deep models. Mostly it's about some mathematical equations that are going on, and those mathematical equations will going to give do some great magic of this generation and such part. And technically, it's just the starting. Because more complex things will come later. Like when we go with the RNN. So RNN is vanilla RNN is still easy, but when we introduce the notion of memory there with the LSTM and the GRU, then it becomes a little bit more difficult. And then when we go with the transformer architecture and all, then imaginary things will get a little more hard. Because in the end, it looks like just simple mathematical equations. But they all, when they combine together, they do this great magic of generating things. So will need some time for you guys to process it. It's not going to get digested in one go. So maybe you can try out some visualization if you are able to find on Google, or maybe some videos might be there for visualization that you can check. Okay.
So like
Sure.
even for the generator also, it is not actually taking the samples data. It is generating from the random, and discriminator is basically taking from the samples.
Yeah, discriminator takes our data set. For the generator, it's just going to take something from the noise only. Okay.
Yeah,
The samples
understood
are
it.
directly fed to the discriminator only. The real samples that are not seen by generator. Okay. Generator does not see our real data set, never. Okay. Only the discriminator sees our real data set.
And the so-called noise is nothing to do with the sample, or it is something to do with the
No, no,
sample.
no. Noise is just we are sampling from the, let's suppose, Gaussian distribution. So that's our noise only.
Random
So
things, I think.
Yeah.
nothing to do with the data set or
Yeah.
this. Okay. Why
So
it should be taken from Gaussian, or it can be taken from anything, or
Gaussian
any
is
specific
uh,
reason to go with
the
Gaussian?
Gaussian is generally gives us the good result, and it's smoother.
Okay.
Okay.
So only empirical.
Yeah.
Okay.
So, but basically we are like initializing the generator only, but after that it will not take from the noise anything.
Sorry.
So basically, we are initializing the generator with the noise.
No, it's all for outputting. Generator always going to take the input from the noise only. Okay,
But
that will
you
be
are
your.
using that discriminator to update the generator weights also in that
No. We are
T.
now okay. In the generator training, yeah, we
Yeah,
use the discriminator to update the weight of the generator. Okay, but
yeah.
at that time, the discriminator weights are freezed. They are not going to get updated.
Okay, understood. Okay, understood.
Okay.
Yeah,
In
understood.
both the alternate training part, while training one, we freeze the weight of other. Okay. Yeah. So yeah, I don't know how long it's going to give. Okay, so
And
few
speed
more.
up?
Sorry.
You cannot speed up
No, I'm not.
like
Okay,
a fast
can
or
we?
like that.
Okay, just label it here.
Just simulation, right?
Yes, we the optimizer different. We mean that uh, you can use this if we are talking about we use the Atom optimizer here for both of them, but we set them in the different variable. Okay, so like I shown here. Okay, so we use the Atom optimizer for both of them, but set in a different variable. Because if you're going to set them in the same variable, then both of them will get updated together. And because we want to update both of them not together, we want to do that like while updating one, the other should not get updated. That's why we set both of them in the two different variables. Okay, so one optimizer variable for the discriminator, one for the generator. Okay, so 9,000 networks. Okay, sure how long it's going. Yeah, you guys can play along with that. I'm going to give you the link as it can take some time.
Sure. Yeah. Thank you. Thank you.
The generator generally takes some time to change. So I have some final points to discuss that are like some problems in the GAN and what are the some solutions that are proposed over the time for the GAN. So one major problem is the mode collapse. Okay, so mode collapse basically means the generator will produce only one type of images. So what does it mean by one type of image? If I take the example of our MNIST dataset, okay, it has the images from 0 to 9, right? Like handwritten digits from 0 to 9. Okay, now it can happen that our discriminator is not able to correctly classify the image of, let's suppose, 5. Okay, that it is struggling to correctly classify the image of 5. And what my generator will do, it's always going to create the fake image of 5 only, because uh, for the 5 image, the discriminator is not able to generate well. Okay, so that is something that can occur, the mode collapse, that the generator learns to generate only one type of images because the discriminator is struggling to discriminate with that type of image. Okay, so I will not get a this uh, variety of the images. In that case, you will get only one kind of images. So that's one problem that the GAN faces. Okay. Uh, Another is the vanishing gradient problem. Okay. So the same thing that happens generally in the case of CNN or ANN. The vanishing gradient problem can occur. Another is the convergence is also a issue in the GAN because as I said, the discriminator may become good easily because initially discriminator will have very good chance of separating the discriminator output and the the output from the real image and the fake image. Okay, while generator needs some time to get trained to generate a good quality of image. Okay, So if we do not set the learning rate appropriately, then the discriminator will be able to dominate the output, or it will be such dominating that the generator will not be able to train well. Okay, so what we generally do to tackle this problem of non-convergence is we set the learning rate for discriminator to a low value, then the generator. Okay, so for the discriminator, we set the low learning rate. Okay, so that it takes some time to train. Okay, while for the generator we set a little high learning rate. Okay, so that's one solution for this problem. Okay, so these three are the kind of the major problem that the GAN face, but one of the major is this mode collapse. Okay, that generator only produce one type of images because discriminator is struggling to produce that type of image. Okay, the other two are more likely the general problem. Okay, now some solutions that are proposed over the time. Okay, basically there were some changes that they did in the GAN architecture. So three main architecture that was discussed, but briefly you can know. Okay, so one is the DC GAN, deep convolution GAN, that basically was used to stabilize the process of the GAN training. Okay, so in which the major changes was that they replaced the pooling layer with the stride convolution. Okay, so they use a downsampling and they use transposed convolution. Okay, now this is something that we have not studied, so and not the scope in the course also. And they use batch normalization. Okay, it's the same one that we studied. And they use the leaky ReLU in the discriminator and ReLU in the generator. Okay, so they made some configuration changes in the original GAN network. And what they were able to do in that case is they were able to make the GAN training more stable. Okay, now WGAN, that was the Wassertian GAN. Okay, this was the solution for the mode collapse, okay, which was one of the major problem in the GAN. So what it does is it has changed the loss function a little bit, in which it includes the Wassertian distance. Now this is also it's not in the scope of our course. So some kind of distance matrix that they use between the real and the fake distributions. Okay, so it includes this distance to capture how close my real image to the fake image. Okay, so with that, it encourages the generator to produce more diversity of the images. Okay, not like just because one type of images is not able to classified by discriminator, so it's not going to generate just that type of images. It's going to create more diversity of the images now. That was the thing that was done by WGAN. Okay, now StyleGAN, that was proposed by NVIDIA. Okay, this was the state of the art GAN network that was the success for that was that it was able to produce high quality good images. Okay, so it has used quite a lot of thing. And after the StyleGAN, there was StyleGAN 2. I think that comes in 2019 or 20. Then StyleGAN 3 was there. That was in 2021, I think. Okay, so more variant of the StyleGAN was also come. Okay, but the basic idea with that started was they use something called as the mapping networks. Okay, so what they started is we start with this Z. Okay, now we will do some kind of linear transformation. Okay, and we will achieve at some intermediate state called W. Okay, so we'll come at some intermediate latent space W. Okay, now this W is less entangled and it's reduced the correlation with our noise. Okay, so it has learned something till now. Okay, now from this W, we create some multiple style vectors by doing the affine transformation. That is by adding some different kind of base bias. Okay, you can get the affine transformation. okay, to get different style vectors. Okay. Then the second thing that it uses the synthesis network. Okay. So this is our generator. Okay, all of these changes that mostly we have studied. Okay, these were only related to the generator part. Okay, because the discriminator there was no much big of the change. Okay, so all these changes that we did was mostly in the architecture of the generator neural network only. Okay, so the second part for this was the synthesis network, in which what we started with is we will take the learned constant input, not the Z1, we will take this W. We will have some convolution layer. Then we will have this style modulation. Okay, that is the adaptive instance normalization. Okay, now of course this is also not in the our course. Okay, we have not defined what does it is, and then it inject the noise. Okay, for variation. Okay. So this is just the prof has discussed it theoretically. Okay. Yeah. So these were the changes that they did. And of course, it can be like what does this mean and what does this mean by noise injection? Okay. So maybe I can use that image on that. So for the style gain, we started with the Z. We come to some intermediate state W. Okay, that was our mapping network. Okay, now from this W, we will create some style vector. Okay, different style vectors were created using the affine transformation. Okay, and then we will having this synthesis network. Okay, in which we'll be having the constant input, then the convolution layer, then the adaptive instance normalization, and then the upsampling part will be there. So in this, yeah. So before passing the our input to the convolution, we add the noise. Okay. Then after the convolution layer and the adaptive instance normalization, we add this style vector, the style vector that we created here. Okay, that is added here. So this is one block of synthesis network that is done here. It's the full image that we have. Okay, so this is how the StyleGAN network was created, and it was able to produce good quality of images. Okay, so a few examples are here. Okay, so that's basically end our summary on generative models and the GAN.
So, sir, are these real images or fake images?
Fake. These are the face generation by StyleGAN. Okay. Now after this StyleGAN first version, they proposed 2 and 3 second and third version also for the StyleGAN in 2019 and 2021. And after that, now diffusion models have taken place. Okay. So to summarize, we have seen our generative models, okay, which learns either the probability distribution for our data or it learns the mapping from the low dimensional space to high dimensional space. While for our discriminative models are basically the models which basically learns to classify the data. Okay. In the terms of generative models, we have seen the GAN only in this week. Okay, which learns this mapping from the latent space to high dimensional image dataset. Okay, and how it does is it goes with the game of Arctic versus the critic, in which our artist is our generator, which is going to produce the fake image, and then we will be having the discriminator, which is going to tell us whether this image is the real image or the fake image. Okay. The goal of the GAN is to reach the Nash equilibrium state in which the discriminator is not able to distinguish between the real image and the fake image. Okay. The main challenge in the GAN is the mode collapse, in which generator is only generating only one type of images, in which the discriminator struggles to discriminate it, or the vanishing gradient problem or the non-convergence problem. Okay, and the different architectures like DC-GAN, which is used to stabilize the training, WGAN, that was used to tackle the problem of mode collapse, and then StyleGAN, it was used to create more high quality, good resolution images. Okay, so that's the
Sir, is a style GN implementation being discussed someday?
no, it's just this week is fully theoretical only. Okay, so this entire week mostly we have discussed the concept theoretical wise only. Okay, so only one simple implementation of vanilla GAN structure. Vanilla GAN, I mean, we will be having a small network for the generator and small network of the discriminator, and Prof will show one training loop for how this training works. That's all is there in the implementation. We do not have any other specific implementation this week.
So we have discussed only GAN, right? Not style GAN.
Yeah, no. Only from the architecture point of view, we have studied that,
Okay.
not more than that.
And in the 6th week sessions, style GAN will not be discussed, right?
No.
Okay.
Yeah. Okay. So, yeah. Any more doubts?
In the coding, the loss for discriminator is BCE loss, no? And for generator, what loss we saw?
See, for the same loss we are using there, PCE loss only, binary cross entropy.
Okay.
Okay. Yeah. Good night.
So, but is a style GAN discussed in the implementation part in this entire course?
No.
Okay. Like, okay, so like, had a small question.
Yeah.
Home personal computer can generate a style GAN a range of pictures. It can be done, sir.
Style GAN pictures. Okay. So you need the good quality of data. You have, and mostly with the computation power that you have, you might be able to do some quality of images you will be able to generate.
Okay, with
Not
the computational power available in an average home, is it possible?
with that cloud resources that are there on the Kaggle or in your Colab. Okay, with using those GPU, you can surely do.
Okay. Oh, thank you, sir. Thank you.
Not with fully high quality, but some okayish quality you can generate.
At least 720p can be.
Not cannot measure that how good it will be.
Okay.
Of course, that depends upon the training configuration that you are going to use and the
Okay.
hyperparameters and all. So many factors are there that are dependent.
So like the offline way of doing without collab or something in any average household
On
computer.
CPU, training these network will take very large amount of time because even on GPU it takes some good amount
No,
of
no.
time.
PC equipped with a GPU in an average home GPU, like maybe something NVIDIA GPU something.
Then you should be able to do it. Okay. But of course, cannot guarantee that how good quality image you will get.
Okay.
But yeah,
Okay, sir. Thank you, sir.
yeah. Okay, welcome. Please fill out the feedback form that I've shared in the chat. And that's all for today. If you do not have any more doubts.